Hello class, welcome to the Stat 215 Lecture 13 video. In this lecture video we are going to learn and discuss about two continuous distributions. First we're going to talk about the uniform distribution, and then we will talk about the very important normal distribution. Let's get started by talking about the continuous uniform distribution. So the continuous uniform distribution is the most basic continuous distribution. Now for us, probability density function of a continuous uniform random variable x can be represented by f of x equals 1 over b minus a, where a is less than or equal to x, which is less than or equal to b, and then we can have it as 0 otherwise. This forms a rectangle with base b minus a and a height of 1 over b minus a. So let's take a look at an example. Let x have a uniform distribution on the interval from 1 to 3. Then f of x would equal 1 over 3 minus 1, which would simplify to 1/2, on the bounds of 1 less than or equal to x less than or equal to 3. So if we wanted to show this visually, we have our x-axis with our bounds from 1 to 3. Along our f of x, or y-axis, our f of x we know is going to be equal to 1/2, and we draw a straight line because it is a continuous function, and it is continuously 1/2 from 1 to 3. And of course, 0 otherwise. When looking at the uniform distribution, we can represent this with a capital letter X, that tilde, and we will abbreviate it as UNIF, and then parentheses are two parameters A and B. So we would say it that X follows the uniform distribution from A to B. The mean for the uniform distribution, or the expected value of x, is a plus b over 2, and the variance is b minus a quantity squared divided by 12. So if we're going to use this example that we did in the previous slide, then our expected value would be 3 plus 1 over 2. 3 plus 1 is 4. 4 over 2 would equal 2. And our variance would be 3 minus 1, which would equal 2. 2 squared would be 4, and then 4 over 12 would simplify to 1/3. So in that case, the expected value would be 2, and the variance would be 1/3. Let's take a look at a second example. Suppose the length in hours of meetings in a particular conference room has a uniform distribution on the interval from 0 to 4. What is the probability any given meeting lasts at least 3 hours? So for us, we know that our f of x is equal to 1 over b minus a. So in this case, it would be 1 over 4 minus 0, which would equal 1/4 on our bounds from 0 to 4. And it would be 0 otherwise. So in order to find the probability that our meeting lasts at least 3 hours, we would integrate from 3 to our upper bound of 4, 1/4 dx, which would be equivalent to x over 4, which we would go from 3 to 4, plug in, and simplify. So in the case, what is the probability that x is greater than or equal to 3? The answer would be 1/4. If we wanted, we could even draw this out. And then for our f of x, we'll say 1/4. The area would be 1/4. Coincidentally, in this case, both our f of x and our area are both equivalent. That's not always going to be the case. Just a happy accident in this one. Okay, so that's pretty much all I really wanted to talk about with the uniform distribution. It's pretty simple, but what I really want to focus on in this lecture and in the next lecture is the normal distribution. So some things to learn about the normal distribution. It is the most important continuous probability distribution in the field of statistics. It is a bell-shaped distribution and it describes many phenomena in nature, and it is the basis for much of our statistical theory. And it's characterized by two parameters, the mean, mu, and its standard deviation, sigma. We can see a drawing of the normal distribution below. The center is where we find our mean, and then our standard deviation categorizes our width. I cannot emphasize how important the normal distribution is. For those of you who are seniors and juniors, some of you may have encountered the normal distribution in some of your coursework. For those of you who are more towards the beginning of your study, you're likely to see this going forward. This is something, even as my career as a statistician, that I have to use frequently. So let's go ahead and define our PDFs for the normal distribution. The probability density function for a random variable x with a normal distribution with mean, mu, and standard deviation sigma is f of x equals 1 over the square root of 2 pi sigma times e to the negative 1 over 2 sigma squared, which is also the variance, times the quantity of x minus mu and quantity squared on the bounds from negative infinity to infinity. We will write x as belonging to a normal distribution by a capital N and in parentheses mu, comma, sigma. You do need to be a bit careful with this. Certain textbooks or certain professors, they may not always do mu, comma, sigma. They may do sigma squared, so they may do the variance. So you may want to just make sure you're paying attention. But for us, we're going to try to keep it consistent and say mu, comma, sigma or mu, comma, standard deviation. All right, so let's take a look here. We have two normal distributions with different means, but we have the same standard deviations. So what that can mean is that we are going to have those same width when we have that same standard deviation, but the center of our bell curve are going to be in different locations when we have different means. So in some ways, it looks like we almost copied and pasted one of those distributions beside each other. Another option is when we have the same mean, but we have different standard deviations. So in this case, our means are equivalent, so our peak of our curve is in the same place, but you notice that that width of our curve is different. Our sigma 1, our standard deviation 1, has a smaller width than our standard deviation 2, which means our second standard deviation is going to be larger, meaning our data is going to be more spread out, which you can even see visually. And then we can also have a case where if we're comparing two normal standard deviations where they have both different means and different standard deviations. And if we think of like that x-axis as a number line, so mu1 is less than mu2, and we can see that mu1 then is a little bit to the left. The sigma 1 is smaller than the sigma 2, so our standard deviation is going to be smaller for our first normal distribution, so it's going to have a much narrower bell curve as opposed to our second figure. So let's take a look at some of the properties of the normal distribution. So for us, the mode occurs at x, which is equal to mu. The curve is symmetric about a vertical axis through the mean mu, which you were able to see in the previous 3 slides. There are inflection points at mu plus or minus sigma. So at 1 standard deviation on either side of our mean, that's where our inflection points are. And if you're not exactly sure what an inflection point is, it's that part of your curve where, if you notice, at the beginning, we're curving kind of down, and then there's this kind of magic point where all of a sudden, instead of curving down, we're curving to, in the drawing that I'm doing, to the right. That magic point where we go from curving down to curving to the right or to the left, if we were doing it on the other side, that's called the inflection point, and that's the location at 1 standard deviation. And it approaches our horizontal axis asymptotically as we move away from mu. And again, this hopefully was something you should have already had an idea of. The total area under the curve is going to be equal to 1. So when talking about area under the normal curve, again, let us assume x belongs to the normal distribution with mean mu and standard deviation sigma. Then the probability of x1 less than x2 is going to be equivalent to the integral from x1 to x2 of 1 over the square root of 2 pi sigma squared times e to the negative 1 over 2 pi squared multiplied by the quantity x minus mu squared dx. Now, one kind of helpful thing about this, because sometimes doing that full integration is overwhelming, and for some of you that are newer to integration, that could be a very difficult integration to perform. We have this handy dandy rule called the 68-95-99.7 rule. And what it says is that approximately 68% of your data is going to lie within 1 standard deviation of the mean. And 95% of your data is going to approximately lie within 2 standard deviations of your mean, and approximately 99.7% of your data is going to lie within 3 standard deviations of your mean. And this is, again, this is an approximation, but it is a pretty good approximation as you guys are getting started. So at this point, let's take a look at an example to test what we know so far and to get some practice. So let's say a test of depth perception is designed so that the scores are normally distributed with a mean of 50 and a standard deviation of 10. Let x equal score. So first we would like to find the probability of x being less than 50, and 2, we would like to find the probability of x being less than 60. So for our first one, finding the probability of x less than 50. Well, so our mean is at 50, and so logically, if that's our center, that's our halfway point, that means half of our data has already happened, half of our data has yet to occur if we're thinking chronologically. So it's going to be 50%. Because if we're moving left to right, mu is our center. It is the 50% mark of our data. There should be theoretically 50% of your data is to the left and 50% of your data is to the right. Now let's do a little bit harder one by finding the probability of x less than 60. Okay, so for this one, and I apologize, I had to pause the video for a second to get a drink of water. I'm going to recommend that we draw out the normal distribution. Sometimes that's going to help us figure out the problem. So I'm going to approximately draw our normal distribution. We have our 50 at the center, and 1 standard deviation over, we have 60, and 1 standard deviation to the other side, we have 40. And from our 68, 95, 99.7 rule, we know 68% of our data is going to be in that center part. Now, assuming that 100% of our data is under the curve, that means if we subtract 100 minus 68, that means we have 32% of our data unaccounted for. That is less than 40 and greater than 60. So if we go ahead and divide that by 2, that tells us we've got 16% of our data that is greater than 60 and 16% of our data which is less than 40. This point now, this kind of just becomes an addition problem, since we want to know what's the probability of x being less than 60. And that's this point here. And so less than 60, so we're just going to add up everything that's less than 60. So that's the 16% plus the 68%. And that's going to give us 84% or 0.84. So just review. So the probability of x being less than 50 is going to be, in this case, 50%. And the probability of x being less than 60 is going to be 84%. Let's continue with this idea. So for example 2, we're going to assume still that x belongs to the normal distribution with mean at 50 and standard deviation at 10. Now let's go ahead and find the probability of x being greater than 70 and the probability of x being less than 40. Or excuse me, x being greater than 40. So to start off with the third, you want to find the probability of x is greater than 70. As we did before, let's go ahead and draw this out. So we have 50 in the center, 1 standard deviation is going to be 60. As we move to the right, 2 standard deviations is 70. And so now we're at this point, we don't need to go any greater than 70, so we're going to go focus on the left of 50. So 1 standard deviation would be 40. And just for completeness, let's go ahead and do 1 more standard deviation at 30. Okay, so we established earlier that we know 68% of our data is between 40 and 60%. For 2 standard deviations, that's 95. So 95% of our data is going to be between 30 and 70. That leaves 5% of our data unaccounted for to be greater than 70 and less than 30. If we cut that in half, that means 2.5% of our data is going to be less than 30 and 2.5% is going to be greater than 70. So for this problem, we were asked to find the probability of x being greater than 70, and we just found that right here. Probability of x being greater than 70 is going to be 0.025 or 2.5%. Now let's go on to the fourth question. This time we want to find the probability of x being greater than 40. So based on our drawing, we've actually gotten ourselves pretty far ahead. So instead of needing that middle 95% from 30 to 70, I'm going to erase that for a second and think back to what we did before within our 1 standard deviation. So we learned that within one standard deviation, we had 60% of our data. So within one standard deviation, we have 68% of our data. Sorry, trying to talk and write at the same time. And that, as we did before, that left 16% on either side of our data to give us a full 100%. So again, this point, we just come to an addition problem where it's going to be that 68% plus the 16%, which will again equal 84%, or 0.84. Hopefully so far this has been pretty manageable. It really helps if you draw the picture. Now let's finish this example off by trying to find the probability between 40 less than x less than 70. Still working with the same example where we assume x is part of a normal distribution with mean 50 and standard deviation 10. So one more time, so I don't have to keep scrolling, we're going to go ahead and let's just draw our normal distribution. And I apologize, this is not the best of my normal distribution drawings. 50 in the center, one standard deviation to the left, one standard deviation to the right. We've got 40 and 60. And now we have two standard deviations, which becomes 30 and 70. So we know theoretically we want this area under the curve. Now from 40 to 60, that part's pretty easy. We know that's going to be 68% because that's within one standard deviation. Now the issue is going to come in when we're trying to figure out this piece right here. Now there's a couple of ways we can do this, but I'm going to stick to using our 68, 95, 99.7 rule. So we know that within two standard deviations, we have 95% of our data, and within one standard deviation, we have 68% of the data. So what we did before when we were trying to find the percentages on either side, we subtracted from 100. So instead of doing that, I'm going to subtract from 95. So if I subtract 95 minus 68, I get 27. So that means there's 27% of our data is going to be between 30 and 40 and 60 and 70. If I cut that in half, I will then have this one piece, which is going to be 13.5%. So using that new piece of information, I can add that to our 68%, and that will give me the probability of 40 being less than 10, 40 less than x less than 70, which will equal 0.815, or 81.5% of our data should be between 40 and 70. Very good. I highly recommend when you're doing these types of problems, draw it out. It will really help you out. Okay, let's keep going. Talking about our standard normal distribution. A normal distribution can have any mean and any positive standard deviation. However, when when the distribution has a mean of 0 and a standard deviation of 1, it is known as the standard normal distribution. This concept is pretty important. Usually, we use the letter Z to represent a standard random variable. So just to take a look at what this looks like, you still have that same normal curve. The mean is 0, so that is our center point. It is the peak of our curve, and then our standard deviation is equal to 1. So 0 is the center, so as we move to the right, we keep adding 1, and as we move to the left, we keep subtracting 1. The rules of the 68, 95, 99.7 rule still apply. In fact, they are really based on the standard normal distribution. So let's take a look at a third example. So suppose we are dealing with a standard normal distribution. So we let Z belong to the normal distribution with 0 as our mean and 1 as our standard deviation. And now we would like to find the probability that Z is less than 1.27. Now, like with the binomial distribution and the Poisson distribution, we are very lucky when we are working with the standard normal distribution because there is a chart we can use. Now, we can, technically speaking, integrate using the PDF I taught you earlier, but when we're working with the standard normal distribution, using the table is much easier. So let's talk about that now. So on eCampus, I have posted a Z table for your convenience. It is also in your book on Appendix A, and it is tables 8.2 and 8.3, and it's somewhere around page 734 and 735. So how you can use a table to find probabilities for your standard normal deviation. So it is kind of interesting. So with your value of Z, it's kind of broken up. So if you recall, for example 3, we were asked to find the probability of Z being less than 1.27. So using the chart, we're going to try to find the value 1.27. Along the y-axis, you're going to be looking for your first two place values, the 1.2. And then it is along the x-axis at the top is where you're going to find your third place value, or your hundredths place, which is the 7. So using this entry from our Z table, we've got the 1.2 and the 0.07. And going in, we can find our value. And important thing about this is this table shows the proportion of data to the left of our Z value. So same thing we were looking for before. It gives us the probability of less than. So we'll still have to do those tricks that I taught you for binomial and Poisson. So this tells us that our probability of it being less than 1.27 is going to be 0.8980. And this chart, like a lot of the other charts, gives us our values to 4 decimal places. Now, you may be asking, okay, so the chart gives us for the less than, what happens when we need greater than? Well, this is still technically probability, so those probability rules still are going to apply. So the probability of Z being greater than 1.27 is going to be equivalent to 1 minus its opposite, the complement, which is the probability of Z being less than or equal to 1.27. And when it comes to continuous values, we do consider less than and less than or equal to and greater than or equal to be equivalent. So from the previous slide, we know that the probability of Z being less than 1.27 is 0.8980. A little bit of subtraction, and we can see that this is going to be equal to 0.1020. And to show this visually, we have our standard normal distribution. We have our point of 1.27. Areas to the left of the curve is what's going to be given in our z-table. So if we want to know what's to the right, we need to subtract from 1. And I've said it before, I'm going to say it again. When you're working with these types of problems, always draw the picture. It is so helpful and it will help prevent so many mistakes. So at this point, let's go ahead and do another example. We're still going to assume we're working with a standard normal distribution, so we'll let z follow the standard normal distribution, mean 0, standard deviation 1. In this case, we would like to find the probability of z being less than negative 0.52. So if we go ahead, look at our drawing, 0 in our center, we've got 1 going up for our standard deviation, subtracting 1 as we go to the left, as again part of our standard deviation, and between 0 and negative 1 we would have our negative 0.52. And lucky for us, as we've established, when we are asked to find less than when we're dealing with probabilities of a normal distribution, that is great because that is exactly what our table shows us. So we should be very easily able to find the area under this curve. So because we are trying to find the probability of z being less than negative 0.52, along our y-axis, we're going to be looking for that negative 0.5. Along our x-axis is the 0.02. Using the table, we can now easily see that the probability of z being less than negative 0.52 is going to be 0.3015. Pretty easy, right? Let's take a look at another example. This one's going to be a little bit harder. So once again, we're assuming z follows the standard normal distribution, and this time we want to find the probability that negative 1.45 is less than z, which is less than 0.42. Okay, not a problem. We can still use our table. So what we're going to want to do is we're going to subtract the smaller area from our larger area to find our area in between our two values, which basically, if you remember the way we've explained this before when we talked about the binomial and the Poisson, what we're going to have to do is find the probability of z less than 0.42 and subtract it from the probability of z less than negative 1.45. Because our table is going to give us the area that's to the left, so everything that I'm kind of highlighting in orange, and we are going to subtract the probability of z being less than negative 1.45, which is this part I'm going to highlight in blue, which will leave that remaining part we care about, which is from negative 1.45 to 0.42. And that's really what this slide 30 explains, that if we use the table and find the area to the left of 0.42 and we subtract it to the area to the left of negative 1.45, we would get 0.6628 and subtract it from 0.0735 to get our final answer of 0.5893. Now, sometimes we are going to have to use our z-tables in reverse. So far, we've been finding areas under the standard normal distribution from a given z-score. So we said find the probability of z less than this. That's not always going to be the case. Many problems require us to go in the reverse direction. So that is, we are either given the area and then we need to find the z-score that corresponds to the area under the standard normal curve. So let's talk about what that actually looks like. So what value of z has 10% of the area under the curve greater than it? Would be one example. So for us, that means we're going to have to find an entry in the z table that is as close to 90% as possible. Because remember, that table gives us to the left of the curve. And so even though we want to find 10% to the right, we have to think a little bit opposite. What is the table going to give us? Well, it's actually only going to give us to the left, which is this 90% in white. So if we use our table, we can see that the probability of z less than 1.28 is going to be equal to 0.8997, and the probability of z less than 1.28 is going to be 0.9015. So that's going to get us close to that 90% that we're hoping for. The 1.28 is a little bit closer, so we're going to let our z be equal to 1.28. Again, this is just a little backwards way of using the chart than we did before. Let's take a look at another example, hopefully to make this a little more clear. So in this case, we want to find the 26th percentile of our standard normal distribution. So we want to find it at 26% to the area to the left of the curve. So meaning we want to find z such the probability of z less than z equals 0.26. So when we take a look at our z chart, and this is an excerpt of it, we're going to want to get as close to 0.26 as possible. We're not going to be able to get it perfect, but again, as close as possible is what we're going to be hoping for. So as you can see highlighted, the closest we're going to be able to get to 0.26 is right here. And so that's going to leave our z value or z-score to be negative 0.64 to be our 26th percentile. When you're doing these problems, make sure you're thinking and reading carefully. Do not rush. Rushing is the enemy of these types of problems because it's the wording that matters. Okay, so to wrap this up, let's take a look at one more example and then let's do our summary slide. So we want to know what's the value of z has 68% of the area to its right. So it's this part shaded in blue. Issue for us. The z table gives us area to the left. And I'm writing this down. So what are we going to need to do in order to solve this problem? Well, to start off, we're going to have to subtract 1 minus 0.68, which is going to be 0.32. That is the value that is to the left of the curve. That's what we need to find in our z table. So in our z table, again, still looking at this little excerpt, we want to get as close to 0.32 as possible, which is going to be right here at 0.3192. So that means our z-score is going to be negative 0.47. And again, I'm going to emphasize it one more time. Make sure you draw the picture because sometimes it can get a bit confusing when you're trying to logic the problem out. Like, oh, should my answer be positive or negative? If you draw it out, it's very, very helpful because if you're drawing it and you can see that the area is going to be to the left or the right of your center of 0, it can kind of give you an idea. So for example, in the problem we just did, I can see my z value is to the left of center, so I know that's it has to be to the left of 0, meaning it has to be a negative value. Okay, so at this point, let's just take let's summarize what we've done so far. I think this was a pretty complicated lecture, especially compared to some of the previous ones. So we are going to stop here, but let's just go over what we've learned. So the first thing we talked about was our uniform distribution and how it is constant over our interval from a to b. We learned about its PDF, which is f of x equals 1 over b minus a from a to b, and it's 0 otherwise. We learned about the normal distribution and how it is characterized by its mean, mu, and standard deviation, sigma. We learned how we can find areas under the curve using the 68, 95, 99.7 rule. And the big thing we learned is we learned how to use our z-table to find probabilities for standard normal random variable z. All right, that's it. As always, if you have questions, send me an email. Have a good night.